This conference will now be recorded.
Good morning, everyone. So today we'll be starting our discussion on sliding mode control. And myself is Bharani Chandra. And you can, for more details, you can go to the web page. Today we'll be discussing the. Let me keep this one here, and if you can, I will slow down. Sorry, yeah. So today we'll be discussing the sliding mode control. The two references what we are going to follow for the theoretical aspect. The first one is Christopher C. Edwards and Sarah Spurgeon, sliding mode control, theory and application, CRC Press. And the second one by Yuri Schitzel, Christopher Edwards, Friedman, and Levin, sliding mode control and observation, your Springer. These are the two books. Mostly we will be going through the first chapter of these books, so which are the fundamental things. The first chapter only will be going through that. To start our discussion, we will continue our discussion from where we left yesterday. So the robust control, not all control systems are robust. Not all control systems have capability to deal with parametric uncertainty inherently. Not all control systems, may I ask all of you to mute please? Sagar and Sagar. So not all control systems what you design are effective in the presence of the disturbance. So basic steps for the sliding mode control is a sliding surface design, which is generally represented by sigma, Lyapunov function, reachability, finite time convergence, and the control system design, control design to drive the sliding variable to 0. So these aspects we will see. We'll start with a fundamental question of why the sliding mode control is required, or what is the importance of Prasad. Prasad, could you please mute?
Yes.
Thank you. So these are the things. So we'll start with the fundamental questions by asking ourselves why sliding mode control is required. And what is Prasad? Could you please be on mute? Thank you. So we will ask ourselves the fundamental question why the variable structure control is required, because sliding mode control is one such techniques in the variable structure control. If you heard the bang controller, and these all comes under the similar category. So the variable structure control, we'll start our discussion with a simple linear system, which is called as a double integrator plant. Double integrator plant. So that means if you see two integrators, if they are connected in series, one integrator is 1 by s, the another integrator is 1 by s. If you connect those two in the cascade, the corresponding system we call it as a 1 by s square, or the double integrator plant. Why this plant is very much important?
Excuse me, sir.
Yeah, Patnaik?
This resound.
Yeah. Resound means somebody is kept in the mute, that is not in the mute. That's why the resound is coming. Is it okay now, Patnaik?
Yes, sir. Yes, sir.
Okay, I think, but if the people are not in the mute, if any one of you, then it will create the resound and it will be the disturbance to everyone. So that's why I am asking everyone to please be on mute. Okay. So why this double integrator is of much important? is much important for the practical applications or any control system design. The beauty of this double integrator, if you see, 1 by s square. So two poles at a origin. So if you can see, there are two poles at a origin. That means the system is unstable system. The second thing is, most of the systems in a very simplified form can be represented by the double integrator. For example, the displacement, velocity, and acceleration. If you see, each of them are, if you differentiate one, then you will get the another parameter. If you take two such parameters, then if you convert it to the time domain, you will get the double integrator structure. The ISRO's launch vehicle can also be represented with the double integrator plant. Simple pendulum can also be represented by a double integrated plant. That means it can be approximated by a double integrated plant, and so on. So this double integrator plant is a unstable system, and many of the systems can be approximated, their characteristics by using this double integrated plant. So now, if I write in the differential equation y double dot equal to u of t, if I take the Laplace transform on the both the sides, then it will become s square into capital Y of s into u of s. And if I transform y of s by u of s, you will be getting 1 by s square. But this is not of our interest. Is my voice is clear? Can you please type in the chat box?
Some resound is coming, sir.
Patnaik, is it? I think only for you. For others, I think Dandis, Sirisha, Kusma, I think it is fine for you. I think Patnaik, this is problem from your side. Please rectify it. Okay. So the initial feedback control, law.
Sir,
Please put it on mute. Satish Naidu. Yeah. Half of my time is going. Okay. So I will start with the linear initial feedback control law. The two such feedback control laws what we have discussed in the earlier lectures are pole placement controller, and the second one is the LQR controller. You can either design, by using any of these methods, either the pole placement or the LQR controller or any such thing. U equal to minus kx, that's what we have seen. If you see this double integrator, there are two states. So my control law, I can write it as, this is the feedback law. This is not exactly the state feedback law. This is the feedback law. U of t equal to minus k into x.
Sir, sound is not coming.
Madam, here is power failure is there, madam. Just wait, sir will come again.
Okay, okay.
The double integrated plant, and the initial feedback control law we are going to select is u of t equal to minus k into y of t. So the important thing to note here is that the k should always be positive for the stable system. Why the k should always be positive for the stable system? Because of the negative. The k, if it's positive, then minus k, since that minus is there, so that will ensure that the eigenvalues will be on the left half of the plane. And since the eigenvalues will be on the left half of our plane, the system will give us the stable response. So that is one such thing. Secondly, if you consider the unstable control law, if you select u equal to minus ky, if the k become negative, then it looks like an unstable control law. That's why you have to ensure always that k is strictly positive if it is scalar, or strictly positive definite if it is a scalar, or strictly positive definite matrix if it is vector, if x is a vector, if it is not the scalar. So what we will be going to do this thing is, first of all, there are two controllers we are going to design. One is the feedback controller. The second one is variable structure controller. In the feedback, as far as the feedback controller is concerned, it is equal to minus ky, which is linear in nature. So it is a linear feedback controller. However, we will see why this linear control law is not enough. We'll see why this non-linear feedback control is not enough to deal with the stability, to ensure the stability in the presence of various initial conditions. If the initial conditions are 0, and if you want to do some tracking, then it will ensure. But however, we are going to see that it is not always possible that this simple linear feedback controller will drive your states to 0. So that aspect we will be going to cover. And the another one is, we will see, if you take two different initial feedback, initial values and the feedback controller, though they might not drive your states to the initiations, however, they have the capability, if they combine together, it is possible to drive your initial states to the origin. So we are going to see that particular aspect. So let's go to the next slide.
Sir, can you repeat that slide again? There is a lot of voice break in between.
Okay, I will repeat. Just in a minute, I will just repeat the thing. Okay, so consider the double integrated plant 1 by s square, and this is linear. This is the structure double dot equal to u of s. Why we are saying it is a linear double integrator? Because if I take the Laplace transform on the both the sides with zero initial condition, then this will become s square into y of s and u of s. If I bring on the other side this s and this s square, that will become 1 by s square. So, and the initial feedback control law, what I'm going to show you here is the u equal to minus k into minus k into y. This is the piece, and we will see that is why this is not sufficient to. So what we'll assume that the k is strictly positive for the stability. K is negative, then u of k will become k into y. So that means you'll be placing the pole on the right half of S plane, which is not required. So for the left half of S plane, ensure that k is strictly positive. By pre-multiplying equation 1 and rearranging, we get y dot square plus ky square equal to c. So this is quite straightforward. You can do it on your own. So you can just pre-multiply, and if you rearrange, then you'll be getting like this. So what is the properties of this particular? This is quite familiar if you consider some k equal to 1, and if you leave this, it represents the equation of an circle with the radius the square root of c. If I assume k equal to 1, based upon this, we change this k value, then the circle might change to ellipse, and so. So for various values of k, we'll get different responses. That's what I told. We'll be considering two cases. In one case, we'll keep the k in between 0 and 1. And in another case, we'll take k is greater than 1. So two different cases, and we'll see what is going to happen. So this is which I'm this topic.
Hello, sir.
Because it's very
Hello.
important. Yeah, hello.
Sorry to disturb you, sir.
Hello.
Sir, your voice is breaking, sir. We are not able to clearly hear you.
Okay. So just give me a minute. Change to Wi-Fi. ఎందుకు వస్తున్నావు? Am I audible? Hello.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Again, I will repeat this for a minute. So this is a double integrated plant, and u of t equal to minus ky of t is my initial feedback controller. If I rearrange, I'll be getting the equation of the circle with c as square root of c as the radius of the circle. For various k values, we'll be getting different responses. So this is one such thing. If you can see that u of t equal to minus k1 of t, if I take the k1, if it is lying between 0 and 1, I'm getting some kind of this ellipse. and this is the case 2, this is getting another ellipse. However, you can see here that this is called as a phase portrait. This is not the time domain plot. Phase portrait means plotting one state with respect to the another state. So you can see that here in the x-axis, x1 is my state or y. In the y-axis, x2 is my state or y dot. So this is one such case for one value of k1, and for another value of k1, you can see that another value of k1, it is again a ellipse and other things. But both are not enough to drive your initial state to 0. So this reflects that if I use the same controller in the time domain, it will give me an oscillatory response. So important thing to note that what I want is if I starting from some initial condition from here or here, eventually after certain time, it should go to 0. The initial conditions, the control law should drive your system from initial conditions to 0. So in both the cases, you can see that it is not capable of doing that thing. So that's why this linear control is not enough to drive your control system controls for your plant states to drive to 0. Now what we will do is we will use now the simulations with VSC. So we will design variable structure control, and how we are going to select is this is the control law. You can see that the control law, if I select, there is a typo, this is y into y dot. If y into y dot is less than 0, then if I am selecting minus k1 of yt, otherwise k2 of yt. How did we get this is a big question. This we are going to answer in the coming slides. If I use this control law, I will show you how to write the MATLAB code for this one. If I use this particular control law, then I will show you what is going to happen. So this is one such control law for one case of k1 equal to 0.005 and k2 equal to 10.5. So in this case, what is happening for these k values? The initial value for the x is, or the x1 is minus 0.2 and the y1 is 0.1. So the two states, one state has the initial condition at 0.2, minus 0.2, and the other state initial condition is 0.1. So the trajectory as time goes, you can see that it has starting like this and it has come down here and it has settled at origin. If I change the k values to different, if I just change the k values, I'm going to see what is going to happen to my states, to my phase portrait. So this is such thing. So if I change the k values, whatever, you can see that k1 equal to 0.5 and k2 equal to 1.5, then what has happened here is it has started from 0.1 and slowly it has started moving. It is spiraling, and eventually it has come down to the origin, and it will stay at the origin itself, whatever whatever the time you keep on running this simulation. So it will keep on. So this aspect we are going to see in the simulations. So what we are going to do here is, the first thing we are going to see, we are going to simulate this double integrator plant. And the control law, the input to the double integrator plant will be giving as minus ky. Two different values of k we are going to do. So total there are three different cases. The first and second case are with the linear control law. In the first case, we are going to use the k1 for the value of k between 0 and 1. In the second case, we are going to use the same control law with k2 is greater than 1. In the third case, we are going to use this is called as a variable structure controller. The structure of the control itself changes based upon this y into y dot. So this is the basic Simulink diagram. You can see that Simulink diagram here. So this is the control law. So for the first two cases, u equal to minus ky for k1 in one case and k2 in another case. This is the double integrator plant. You can see that there are two different integrators. So one will give you one state x1, if whatever here getting is x1, whatever here getting is x2, and this is x2 dot. and x2 dot is nothing but equal to y double dot. So here the states, I'm trying to see how the states will look like. So what is inside this control law and how to code, I will tell you. It is very easy to construct a double integrator, take the two different integrators from the Simulink and place it. So this already we have done. And this is the embedded function. This already we have done. This k1 and k2 are the constant, and the selections will tell you which one to select. I will show you a tiny piece of code which will, which will educate us on how to do the simulation. So the first thing here is I have written two different types of code. So the first thing is this is BD close L, close all, CLC clear. This is just the standard things. So to demonstrate this controller how it is working, so the initial conditions are the one which is required. You can see that the initial conditions 0.1 and 0. minus 2, sorry, minus 0.2, and the k1, the k values I have considered as 0.005. That means this is the first case where the k1 is between 0 and 1, and the second case k2 I have taken 10.5, and the time, this time will tell us for how much time I have to run the simulations. I'm running for 500 seconds. There are three different cases. The first case is the prompt. If you run this one, it will ask you to enter 1, 2, or 3. So the selections, whatever you have seen, so it will take the input from this prompt, whatever you are going to enter. If selection equal to 1, then it will run this one simulation. Based upon if it is 1, it will consider the case A. I will tell you how it is going to take. If the selection is 2, it is going to run case B. If it is selection 3, if it is not neither of 1 or nor 2, then it will run the sliding mode case. This tiny piece of code I will be giving you, but if you are running the older version, this I have ran in the 2018. If you are running in the older version, then just replace this SLX with MDL. And in the older case, if this prompt, if this doesn't work, then what you have to do is you have to comment out these two things and just write selection equal to 1, selection equal to 2, selection equal to 3. So whatever, if you are writing selection equal to, you remove this prompt here. If you are typing 1, if you run, it will take the first case. If 2, it will take the second case. And if you type any other thing like 3 or so, it will take 3. If you are typing 3, it will take the third case. And this is for the plots. So it is going to plot in the x-axis the states, state 1, and y-axis the state 2. And this is the labels. Yeah, so this is now you can see the control, how the control look like. So as I'm saying, if in the first case, if it is the first case, selection equal to 1 minus k1 into y. In the second case, minus k2 into y. K1 and k2 are already we have seen in the parameter file. And else, you can see that the control law, what it is saying that if y into y dot is less than 0, there is a typo here. Instead of y dot, the dot has come on the greater than. So forgive me for this one. So if y into y dot is less than 0, it should take minus k1 into y, and the otherwise it should take k2 into y. So that's what it is happening. You can see here, if y into y dot is less than 0 and u equal to minus k1 into y, then it will be if this is the condition, if it is satisfying, then what we'll be getting, u equal to minus k1 into y, otherwise k2 into y. To run this code, the input arguments required here are k1, k2, y, y dot, and selection. So that's what you can see, that k1, k2, y dot, and selections. So that's what it is happening. So this is what you are seeing here is y dot you will be getting. So y dot is nothing but you are getting from here. And if you integrate this y dot, you will be getting the y. So that's why the y is coming here. So this is a tiny simulation. So what I'll be doing is I will give you a skeleton code now. The meaning of the skeleton code I will tell you in a minute, and then you have to do the simulation. And I will be giving you the slide. So what you have to do is you have to copy this this parameter code in one M file. And the second task what you have to do is control block, whatever this control block code is there, that you have to copy and paste inside this control block. So this will ensure that this will end this control block. Just copy and paste. So if you run this, you should get the results. There are two different cases where you may not able to get the results. The first case is if you are using the very older version of the MATLAB, then two things you have to do. You have to replace this SLX with MDL files. I'll be giving you the MDL files as well. So just type MDL here and MDL here. If you're using the newer version, you type it SLX, or otherwise with the MDL, the old file can run in your newer MATLAB as well, newer versions as well. The second thing is, if this prompt doesn't work, just comment out this prompt and just remove this input of prompt, and you can just type 1 here, 2 here, 3 here. So if you run this particular code in the normal case, it will prompt you to enter 1. If you're entering 1, it will directly give you the plots, what you can see there. So this is the second part of the code. So what you have to do is this one, whatever you're seeing here, is append this figure here. So here in the bottom, so it will look a very big code. You have to append this figure. So if you run this parameter code, automatically you will get all the results based upon if you are selecting 1, 2, and 3. So now what I'm going to do here is I will give you the code, the skeleton code. How the skeleton code will look like, I will show you now, and you have to do that one. But how to run this one, I am just going to show this one. So hopefully I am running the SMC code for the double integrator. The first thing is you have to create a parameter file. So this is the parameter file. What you can see that whatever the code I have given there, you just copy and paste, create one new M file, copy and save with whatever you want. But don't save with the characters which the MATLAB won't allow you to save. Better you can save parameters under parameters.m is the file, and then you can run this one. So this is the code. So this is the initial values, this is the k values, this will prompt you to enter 1, 2, 3, and this is. So this one I'll be giving you this parameter. I'm not going to play a parameter here. I am going to give you the PDF file of this lecture. You have to copy and paste it here. If there are some errors, you have to rectify on your own. And this is the skeleton what I'm going to give you. This file I'm going to give you. So what you have to do is, you don't have to do anything. Just replace this, fill this. You can see that this fill this is the one. So in this fill, you have to copy and paste the control code what I'm going to give you now. So this is the parameter codes, and this is the control block code. And I'll be giving you 15 minutes at 7:20. I'll be sending you this in a minute. So I'll be giving you 15 minutes. So please develop the code. Just copy and paste, nothing more. So since you have already expertise, you have some expertise in already I've sent you the revision of FDP 1.0, and on second, and yesterday also you might have done something. So just copy this control block code in that one and see whether you are getting the results or not. As soon as you get the result, please post in the chat box or the WhatsApp chat that you got the result. So I'll give you 15 minutes to do this tiny task, and so that's it from my side. I will be sending the files in a couple of minutes to you. You will receive in another couple of minutes. The password will be the same for all my PDF files. Bharani GMRIT is the one. So I'm just converting the code for the 2011 version so that it will be helpful for you. So three different files I'll be sending you. So one file is the presentation file. The second file is the sliding mode, that Simulink file in MDL format, and another one is SLX format, the skeleton one. So you have to write the parameter code, and then accordingly you have to do this thing. So it will be in your WhatsApp chat box now. So you can please check your chat to WhatsApp. So I have sent the three files to you. So now it is your turn to do the things. So download the three things, create a parameter file, copy the parameter values there, whatever in the thing, and secondly, uh, in the skeleton code, use that one. And as soon as you get the results, please let me know. This I have intentionally given you the unprotected one, so that you don't have to struggle much. And if you receive, and if you could able to see the similar results what you have obtained, then you can please ping me in the chat box or in the WhatsApp both. Did not open means I don't know what do you mean by did not open. Sir, which file you're talking about? Guys, please be Guys, please be on mute. Otherwise, I'm forcing from my side too. Mr. Samarjit Patnaik, could you please be on mute? Thank you. Some of you have not logged in with your in the format what I told. So forcefully, I have to remove you all from tomorrow onwards. Please ensure that you should log in with your roll number dash hyphen your name. Bhanu, Pradeep, Surya, Amarendra Reddy, Bhushan, Venkatram Reddy, Krishnam Naidu, Kusuma. These are the ones who have not logged in with and the other names after F. Harshvardhan, Home, Padmaja, Vimala Kumar, Srikant, Satya Sai, Ramakrishna, Upendra, Pandya Raj, Pranita, Prasad, Rajesh, Ramakrishna, Ramya. S. I don't know who is this S. S, could you please let me know? Otherwise, I'm just removing you from I don't know who is this S. Please type in the chat box. The remaining names are familiar to me, so I can pick them. And this Home, the remaining are fine. If any of you have obtained the result, please post in WhatsApp or the chat box. I'll wait for another 5 minutes because it seems some participants are still working on that one and some has requested me to give some more time. So another 5 minutes we'll wait and then we'll start the session. Thank you.
Okay, mom.
Hello, sir. It is not audible, sir. Now,
Yeah, hello. Yeah, hi. Kasim, can you please mute yourself? Kasim Shakiru.
Yes,
Uh,
yes, sir.
could you please mute yourself?
Okay, okay.
Thank you. Okay, I think most of us has got the results. If not, then we can help each other in the WhatsApp forum. So we'll start the next session now. So I hope this was quite useful for you to get trained on the simulations, because I will be sharing you with the toy simulations only, this kind of things. And once if you become expert in this one, you can easily solve the journal papers which I'll be sharing at the end of this. Let me share my cam. Problem with my mic. Uh, Okay, so thank you everyone. So now I think we should proceed to the next topic. So can you tell in 30 seconds how was the difficulty level, or could you able to do it? Anyone, just for 10-20 seconds, not more than that. Let me pick the random the new person, Gayatri. Gayatri,
Yes, sir.
could you able to
Sir.
get the result?
Yeah, I got that. I just need to correct the file name and enter that as per the cases what you have given in PDF. So I got the result.
Okay, okay. Raghav Sharma, 2061, 61.
Hello, sir.
Yeah,
Hello.
Raghav Sharma garu. Yeah, hi Raghav
Sir.
Sharma. Could you able to? Any difficulty?
Sir, I have copied and pasted the code inside the control block, sir, but I am getting error.
Okay. We will discuss that part later. Okay, fine. Okay, thank you. So
Okay,
I'll
thank
be
you.
starting the lecture.
Okay.
So just I want to get the
Okay.
random feedback. This is fine. So now I will be going to show you the importance of I am going to share my screen now. Share the screen, the complete screen. So I think my screen is visible now. So what are the lessons we have learned from this particular simulation? The lessons what we learned that if you go with the linear individual two different linear controllers with different parameters, you are getting two types of responses. If you combined both the control laws at different structures, if y into y dot is less than or greater than 0, if it is less than 0 otherwise, so two different structures we are using with the two different controllers. Controllers are the same, only the gains are different and the structure is different. So that's why the variable structure control is coming into the picture. So the good thing about this thing is individually, both of them might look, it's not going to the from the initial condition, it is not going to the origin. When I combine both of them together, then you can see that it is going to the origin. From any initial condition, you can drive it to the origin. In both the cases, you can check with different initial conditions and you can see whether you are getting the same response or not. That is not the case with the linear feedback controller. So this is the variable structure. This is one classical examples which you will see the experts from various sliding mode experts. So both of the text, Christopher Edwards is an author, and fortunately I worked with him for 4 years with when I was in UK doing my postdoc, and he was during my PhD also. He was my team member. So I was fortunate to work with him. So the whatever my learning is from him, I am trying to pass it on to all of you so that it will be helpful. Okay. So now we will go to the crux of the sliding mode controller. If you see, please listen this very carefully. If you can understand this clearly, then I can guarantee that if you know this fundamental very well, then you can replicate the same thing for very complex system as well. Consider the system x1 dot equal to x2 and x2 dot equal to u plus fx1 x2 comma t. The difference between this system and system what we discussed earlier is the main thing is here you can see that the cursor is not visible. Yeah, you can see that this f is the additional disturbance, whereas in the case you can see that this is 0.1 and minus 0.2 and something like this initial conditions what we have seen. U is the controller. That this looks very similar to very same as that of the earlier problem. The only thing is this f of x1 comma x2 comma t. So this is an unknown. This is an unknown disturbance which you don't know, and we will see in how your sliding mode control design will have impact to suppress this disturbance. The only thing what you should know here is while designing the sliding mode controller, the magnitude or the bound, unknown bounded disturbance. So the maximum value of this f, it should be known to you. So it should be known a priori. You don't have to know exactly what is that, whether it is a sinusoid, whether it is a step, whether it is a noise, or whether it is a high frequency noise or such thing. Only the absolute value of or the bonds of that disturbance should be known to you. And I'm saying that bond as L. So now the control design, the control problem is, can I design the controller which will drive the states to 0, which is exactly the same in our earlier cases as well. However, is it possible to attenuate the disturbance as well? And we are now considering here the asymptotic convergence. That means when t tends to 0, my states x1 and x2 should go to 0. That means if you consider t is very large, then during the time your both the states should go to 0. That is called as asymptotic convergence. The another convergence is in the sliding mode, which is quite famous, is the finite time convergence. So is it possible to know? So here when t is going to infinity only can be assured when you are discussing about asymptotic convergence. The second case is, if is it possible as t tends to some as t goes to some finite value, in that finite value can this x1 and x2 goes to 0 is my concern. Here again we will start our discussion with the linear state feedback law. You can see that linear state feedback law. This is the difference between the earlier one. Earlier one is the output feedback law. Why we are calling it as the output? Because u equal to minus k into y. Y is the output. But here the states, both the states x1 and x2 is coming into the picture. Whereas in the earlier case, it is minus k into y. Y is nothing but my first state x1. Okay. And here again, I'm assuming that k1 is greater than 0 and k2 is greater than 0. And the initial conditions I have selected as 1, minus 2, k1 is minus 3, and k4 as 4, and my function is sine 2t. So two simulations we are going to do with this one. One without the disturbance. That means I will assume that this f of t will be f of x1 comma x2 of t will be 0. This one. And next what I will assume that this f of t will take the sinusoid function form, and we are going to see what is going to happen. So this reference I have considered from this textbook, number 2, reference number 2, Yuri, Christopher, Leonard, and Harry 11th. So this is again from this textbook I have taken this one. I will show you the beauty of the sliding mode control in this one. Why one has to go for the sliding mode control. So this is the two simulations. You can see that without disturbance. So that means when I say that f of x equal to 0, so this is very much similar to your older, the earlier one. But what I assume that f of x is 0 and it is a state feedback, u equal to minus k1 into x1 into minus k2 into x2. Whereas in the code what you have done, it is exactly u equal to minus k1 into x1 only. You assume that k2 is 0 in that. So for this particular term is 0. Rather, you have considered two different cases, individual cases. In one case, this k1, and the another case with k2. So this is one. What you can see that in the presence of, in the absence of disturbance, two initial condition. One initial condition is 1, and the another one is minus 2. That's what we are saying, 1 and minus 2. So the blue one is the first state, and this orange one is the second state. You can see that both of them are going to 0. So my linear control is perfect, though it is taking around 4 seconds of time. And my initial control, because the initial states are non-zero, that's why, and hence it need, my control is based upon minus k1 into x1 into minus k2 into x2. K1 and k2 are the gains, or which are given here 3 and 4. So that's why it will start 3 into, plus 3 into 1, which is 3, minus 4 into 2, 8. So minus 8, minus 8, minus 3, that will be minus. So I think it is 5. So that we can see it later. So minus k1 into x1 into minus k2 into x2. If you substitute this initial values, you'll be getting the initial value. So minus k1 into x1, so 3 into 1, -1 and -4 into 2. So if you just sign changes, if you take it, so that will start with 5. So that's why my control law is starting from 5. And gradually it is going to 0. So obviously you can see that when my control law goes to 0, all my states are also going to 0. This is obvious. So I don't need the control once the state is going to 0 because my job has been done. So this is without disturbance. In the next case, what I'm going to do is this f of x, I'm going to consider some sinusoid disturbance and I will see whether the same control law will be the same, and I will see with the response what is going to happen. So you can see what has happened here. Initial conditions are the same, so that's why it is starting from -2 and -5. As soon as I inject the unknown disturbance, though I know the bounds, you can see the properties, the good properties what you have seen in the linear control is completely matched. And the same thing is happening here as well. You can see that though because it has not reached, so that's why there is some does not reach to 0, so that this is also non-zero. So what is the lesson? What we can learn from this one is that your nominal linear control law has a capability to deal with nominal systems or without disturbances. As soon as if you see the disturbance, you can see the good properties or the good results what we have seen in the without disturbance has lost. So this motivates us to go to the sliding mode control design. So what is a sliding mode control? And these are some of the preliminary things what I'll be discussing you. Consider the desired compensated system. Again, I'll be discussing the same system. X1 dot equal to x2 and x2 dot equal to u plus f of x1 comma x2 into t. So consider the desired compensated system. I want, this is my desired system dynamics. Obviously this x1 dot equal to x2 what we have seen there. So it inherently it has captured both the x1 and x2 dynamics here. Plus c into x1. As long as this c is positive, if this is going to the other side, so that will become minus a into x1. That will always ensure that x1 will have the pole on the left half of this plane. That means if you convert this, if you take the Laplace transform, if you rearrange, then it will show us that the pole is minus c, which is on the left half of S plane. So and hence the system is stable, and c should always be greater than 0. That will ensure the stable system. Otherwise, if c is less than 0, then obviously then what is going to happen? Less than 0, if it is coming to this side, then that means you are placing the pole on the right half of the plane, which is not the desired one. So now, so this is my desired compensated system, which is quite straightforward. And x2, this x1 dot is nothing but x2. So now I am introducing a new variable, which is called as sigma. So what is the sigma? So this is the compensated system. What I'm doing is sigma equal to x2 plus c into x1. This is obviously known from you, and I assume that c is greater than 0. So the sigma is a stable variable, and the purpose of is to design a control which will drive sigma to 0 in finite time in the presence of disturbance. So earlier my controller couldn't able to drive the control the states to the 0, but here what we are going to do here is we will design a controller which will drive the sigma to 0 in the finite time in the presence of disturbances. We will use the Lyapunov theory to derive the control system. Since the participants who haven't attended FDP1, for them again I'm revising briefly what is the Lyapunov stability theory in a very brief way. So the Lyapunov theory says that consider a positive definite Lyapunov function. Positive Lyapunov function. I'm considering this sigma. In some cases, you can write it as x or y or whatever it may be. So this is a positive definite. Why this is a positive definite? This is because of the beauty of this sigma square. That means if you use positive value of the sigma or the negative value of the sigma, your v will always be positive because you're taking the square. In some cases, you might be worried why we are taking the half here. In the next step, for the asymptotic stability about the equilibrium point, the following must be satisfied. That means v dot should be less than 0 for all sigma not equal to 0. And as sigma goes to 0, v should go to 0. So you can see that the second property, if I substitute, in the v this infinity, obviously this is also infinity, v is all infinity, this is satisfied. But v dot or the first derivative of this v should go to 0. That means, how do you do that one? That means if I take the derivative of this one, what will this become? 2 into sigma dot, or in some cases sigma into sigma dot. So 2 into sigma dot. So what is going to happen? 2 into sigma dot. This 2 will get cancelled and sigma into sigma dot will come into the picture. 2 into sigma. So into the derivative of that one. So that's why this 2 will get cancelled. So this will become sigma into sigma dot. And for finite convergence, this is the property. So this is v dot equal to, it should be less than minus alpha I into square root of v half. So this, how did I get this one? So this is a very big story which I'm not going to tell you. So this is, just remember, this is a property, finite timing. If you want the asymptotic convergence, then v dot should be less than 0. That means as t tends to 0, as t goes to 0, your states or the sigma will go to 0. If you want the finite time convergence, v dot should be less than minus alpha into square root of half. So this, when alpha is the greatest, if this alpha is positive, then we call it as a finite time convergence. And the sliding mode control will ensure that the final time convergence is designed appropriately. Okay. So now for our particular example, that's what I told. V equal to half into sigma square I have selected. I have taken the derivative. So what will happen to the derivative of this half? Leave it like that. 2 into sigma dot. This 2 will cancel. 2 will get cancelled, and sigma into sigma dot will come into the picture. What is the sigma dot? Again, if you see here, what is the sigma dot? Sigma is defined here like this. If I take the derivative of this sigma, so sigma dot is nothing but x2 dot plus c into x1 dot. So remember this, if I take the derivative of this one, x2 dot plus c into x1 dot, c is constant. So x2 dot plus c into x1 dot, x1 dot is nothing but x2. So that's what it is going to happen, c into x2 dot. And again, if I substitute the x2 dot formula, which is nothing but u plus f2, so it will look like this. So you have to take the pen and paper and you have to do it manually, then only you will get the feel of this. So now what I am assuming that my u, so this u is in my control. What I'm going to assume that u equal to minus c into x plus v. And if I substitute this u here, then I'll get the v dot something like this, sigma into f of x. Sorry, this should be, I think this should be x2. The x2 terms will get cancelled, and this v will be here. And now the purpose is, how should I select this v? If I select v equal to minus rho into sigma sine of sigma, or this is signum function of sigma. From where I'm getting the sigma? Sigma, we have seen the equation, and this rho should satisfy this one. So this, what is this L? L is the bonds on the uncertain bonds. This L, as I told, this L should be known to us, and this alpha is the finite time convergence parameter. So this L should be known a priori, and this alpha can be a tunable parameter. Based upon this alpha, you can find out the rate of convergence, or basically the convergence rate. And and this root 2 is coming from that particular aspect only. Okay. So now we are ready to go for the control design. So this is my controller. So u equal to minus 3 into x2. This rho is L plus alpha by square root of 2. This alpha is known to us. This alpha is the maximum, is the bounds on the uncertainty. So this should be known. If you see this one, sorry, this L is the bond. So this bond should be known to us. I should know what is the maximum value my disturbance, the disturbance can affect my system. So this L
Sir?
should be known as here. Yes.
Sir, excuse me. What is the physical meaning of L? Is it applicable to for all the linear and nonlinear system? L,
Sir,
L.
this L is a, yeah, let me complete, sir. This L means it is the disturbance, bounded disturbance. Suppose if you are operating at speed of if you want to control the speed of a DC motor, and your output is a speed, you should be knowing externally how much the maximum disturbance externally it can be added. Suppose if it is a 1500 RPM, due to some external force, can it go to 1520, 1550, or 1600? So the bond is 100. So the maximum value, the disturbance is 100. That's what I mean to say. If it is a current, if you are operating, let us assume some boost converter, the two states is the voltage and current. So if let us assume current is 1, the output current in general nominal case is, let us assume, is 1 amp. So due to some other external parameters, the maximum value through which, due to the disturbance, external disturbance will act on your current value on your system, so that the current can maximum, it can go to 1.5 or so. So maximum value you should know. So that L tells about the bond. So that is a physical
Okay.
implication.
Okay, sir. Thank you.
So yeah, okay. So this V is generally, if you see that my sliding mode control is a combination of linear as well as a non-linear thing. And this V is a non-linear term, and the this particular term is a linear control law. So this is a combination of linear as well as non-linear. And this minus rho into sigma, sine of sigma, this is signum function. And this rho can be given by L what I discussed, and alpha is the convergence state, finite convergence state, what we have seen here. This alpha is coming from here. So L should be known a priori, and alpha is a tunable parameter. So now one can ask, what is the sine or the signum function? The sine or signum function will look something like this. So let us assume x is my time, or some x is some variable. So if x is less than 0, you can see that x is less than 0. When x is less than 0 in this thing, my output will be -1. When x is greater than 0, my output will be 1. And when x equal to 0, my output is 0. So you can see that for the positive values of x, always it is y. So the y is positive. And for the negative values of x, when x is greater than 0, sorry, this case, when x is less than 0, so it is -1. And when x equal to 0, it is 0. So this is called as a signum function. And the MATLAB command sign of x will give you the signum function. So this tells about, the sliding mode control law. So this V is my sliding mode control law. Now I will formally define the definitions of the sliding mode variables. So this is the sliding mode controller. Forgive me for this typo here, the x2 should come. So that's what you can see, that u equal to minus c into x minus sigma into this one. So this sliding variable, so the sigma what we have discussed till now in sliding mode literature, it is called as a sliding variable. And this sigma is called as a sliding surface. The sliding manifold sometimes can say. Sometimes the sliding manifolds can be a multi-dimensional as well. Instead of sigma, you can have the surfaces. The sliding surfaces, then sigma can be a vector as well. And the condition what we called sigma into sigma dot, we call it as a reachability condition. And the reachability condition, for the reachability condition, this is this thing, minus alpha by rho 2 into modulus of sigma. So it should satisfy this one. So that is called as a reachability condition. So this is the final control law. Now I am going to implement this final control law by using the linear feedback method and the nonlinear method, and then I will see how my response will look like. So this is the block diagram. This is the simulation diagram. So again, I will be giving you the skeleton. The first thing is what is this plant. Only two things you should know. This is the plant and this is the control law. And this is, I have kept the switch here, switching action. If I want to see the response with respect to disturbance, I will activate the switch. If I want to keep the switch to 0, yeah.
Sir, can you please zoom a little bit, sir?
Zoom a little bit, okay.
Yeah, sir. Thank you, sir.
Okay. Yeah. You can see there is a switch here. So this is a manual switch. I have not written any fancy coding. If I want to see the response with respect to the disturbance, I will activate this switch. If I want to activate to 0, if you double click, your switch will be activated. Okay. So this is to see your response in the presence of disturbance or the absence of disturbance. So the next thing is, this is the plant. I think, yeah, this is the plant. So 4 inputs, two are the states. one is the disturbance one, and the another one is the control law. So this is again my second order system. I will show you what is inside this plant and other things. And this is my control law. I have written the single MATLAB code, a single symboling file. This is one way of doing the coding. There are hundreds of way, or there may be a good way of writing the code itself. But this, I feel that for you, this is the simplest way to do the coding. And here there is again one more switch. So there are two control laws it is going. It is linear control law and the sliding mode control law. If you want to see your response with respect to the linear control law, double click this one and it will be connected to the linear control law. If you want to see the response with respect to the sliding mode controller, if you double click, it will the sliding mode controller will be activated. So this is oh, something has happened. Okay. Okay, so this is basically the simulation of linear controllers. I think this block diagram is quite clear. Now I will show you what is inside this. Let me go to the full screen mode. What will be inside of this, how to do the coding. If you see the plant block, we have seen 4 different inputs. One is x1, next one is x2, and at x1, x2, this is the disturbance and u. And this is the standard. So if you see, this is the equations, x1 dot equal to x2 and x2 dot equal to this. Don't type this complex equation in the plant block. So this is just for your understanding. I have typed here. So what you have to do is just to copy and paste the 3 lines. This is for your understanding. So what is happening is x1 dot equal to x2 and x2 dot equal to u plus function. So this x1 dot, I have represented this x1 dot as x1 underscore dot, which is x2. X2 dot equal to u plus f underscore x1 x2. So that is the way to write the code. You can write in any way. This is one such way of writing the code. So this is my plant block. So the plant is very much clear. Now I will go to the control block and I will explain you how to write the controller. The important thing first to see here, there are 3 different inputs. 3 different outputs. For designing the controller, I need 2 different inputs, x1 and x2. This I have written as lin underscore smc underscore control, so linear as well as smc control. U underscore lin means this is the linear controller. U underscore smc means sliding mode controller, and sigma is a sliding surface. So this is the parameters k1 equal to 3, k2 equal to 4, c equal to 1.5. So I ensured that k1 and k2 are greater than 0 and c is also greater than 0. So that's what I want. So this is the linear controller what we have seen. U equal to minus k1 into x1 minus k2 into x2. K1 is greater than 0 and k2 is greater than 0. So that is what. So that is exactly what I have represented here. And the sigma you have already seen, the sliding surface is x2 plus c into x1. This row directly I have assumed as a 2. You can vary this various values of rows. And you can see this L is the bonds on the value of that sinusoid disturbances what I am giving, the maximum value, that range I can see, plus alpha and square root. I have taken this 2. You can take different values based upon this L. If you want to give more large sinusoid disturbance, then you have to give the more value of rho. And this is my sliding mode control, u equal to minus c into x2 minus rho into sigma. It's the sign of sigma. So that's what, minus c into x2 minus rho into sine of sigma. So this is the way to write the linear SMC code as well. So now, so you have seen, so this is the one. So now what has happened here is this, in presence of the disturbance, you can see that this bloody linear feedback controller couldn't able to attenuate my disturbance. So now my sliding mode controller, if I use the same thing here, the sliding mode controller, you can see the properties. So you can see that, so this is exactly, it is following. It has more or less, it has reached to 0. But what is the difficulty in the sliding mode controller? This is with disturbance only I'm showing. I'm not showing with respect to in the absence of disturbance. You can see that something is happening. This is high frequency phenomena. That means your controller is completely switching. And this particular phenomena in the sliding mode control is called as chattering. And how to avoid the chattering? And there are many ways to avoid the chattering. One such way is by using the higher order sliding mode control law. Another way is uh, to approximate the sine function, sigmoid function, the edges of the sigmoid function, and that is another. There are another 4 5 ways which is beyond the scope of this presentation.
Sir,
So this is yeah.
Sorry, you are telling that chattering with high frequency. What is the range of that frequency in a kilohertz or some megahertz? You are just clock frequency.
That
You are just
depends
telling the
upon
high frequency.
that. Sir, please listen, sir. That depends upon the kind of control you are designing. In general, for the practical systems, for any aerospace systems or for any power system, that depends upon the switching frequency of the whole system what you are using. That depends upon the switching frequency of your IGBTs. If you are operating with the IGBTs or any power electronic devices, that depends upon the switching of that one. So this, in general, we try to limit it to 100 hertz for the practical applications by using higher order sliding mode or for by using the approximation of the sigmoid function. So the standard one in the industry is we should limit because that depends upon your Mr.
Hello. Yes,
Be
yes,
on
yes,
mute.
I'm getting, sir. I'm getting, sir. Just disturbance is coming. Sir, some
Yeah, that's why, sir.
disturbance.
Please. So please be on mute, sir. Let me answer your question. If you have anything, you can put it in the chat box. I will be happy to reply that one. So for the practical systems, we generally limit ourselves this switching this high frequency based upon the actuator available. If your actuator, whatever the actuator you're using, if it has capable of, let us assume, 1 megahertz, then there is no point in reducing to this to 10 or 100 hertz. That depends upon your actuator capability, the bandwidth of the actuator what you are using. In general, in a very rough way, in most of the practical application, the actuator, if it is a Moog's actuator, then we try to limit this to 100 hertz. But that again depends upon various actuating devices. If your actuator has the high frequency device which can tolerate 1 megahertz, you can go up to the half of that on 500 kilohertz or so on. So that depends, not 500 kilohertz, half a megahertz or so on. That depends upon your system, your actuator capability. So this is the simulations of that one. So this is the beauty of this thing. I will just run the demo from my side and I will tell you what to do. So you have to run 4 different cases. One, for the activate the linear controller. In the first case, assume that the disturbance is 0. The second case, assume that the disturbance of sinusoid disturbance is activated. The second case, go with the SMC and repeat the 2 cases, one with the one with without disturbance and the another one is with disturbance. So now what I'm going to do here is I will be showing you the simulation. So these simulations I have written in bit different way. Why I have written this bit different way as compared to the previous one is just to give you the flavor of 2 different ways of coding the things. I'll be going to the Chris new book. So first of all, here there are no parameter files. Here there will be one plotting file. This I will give you. This plot file you have to use once if you run the simulation. Okay, so I'll be opening the simulation file. So this is I will give you the skeleton one. So if you see this, if I double click, so since this will be the skeleton file, you don't have this the x1 dot and x2 dot. This you have to fill. And the another one is I'll be giving you the control file. This is empty. Here you have to type whatever the code I have given to you. And for the 4 cases, what I'm going to run here is the first case, I have activated, you can see here, the ulin has been activated. And you can see here, the 0 has been activated. That means I'm going to see the response when there is no disturbance and when my control input is linear. So if I simply run this one, it will run. If everything is fine, otherwise the error will pop out. And then once it is done, once the simulation is done, then I will run this plots code. and this will give you two different things. So you can see that here, so this is the states which is going to 0, and this is the control law, and another one is the sliding surface. So as far as the linear thing is concerned, there is no sliding surface required. Okay, so this is one such case. In the second case, what I'm going to do, in the second case, I'm going to activate the disturbance. So how I will do, I will just double click this one. It has been activated. Now I'm going to run this one. So now again, I will go to the plot and I will plot this one. So now you can see that, this is sliding surface, which is sigma not required. You can see that what has happened here is, you can see that one, it is going the same. So this is the control signal. So what you can see here is my nominal controller couldn't able to drive my states to 0. Now the second case, so two sets of simulation we have done. The linear has been activated, one with 0 disturbance and another with what, and another one is with sinusoid disturbance. And what I'm going to do here is, now I'm going to operate the sliding mode control here. Sliding mode control has been activated. You can see double click. I'm double clicking this one. My, now the sliding mode control with 0 disturbance. I ran this one. You can see that this is running. Don't rush to run this one. Once it is completed, come back here and run this plots. You can see that without disturbance. So this is the sliding mode, and what has happened here is without any disturbances, it is more or less, it is acting like this. This is the sigma. So you can see that from some initial condition, it is going to 0. So this is called as a reaching phase. The similar in the sigma, you can see that up to this, there is a small jerk. You can see that. Why this is happening? Because it is, my sigma has reached to 0 in this particular time, and after that, there is it is perfectly fine. So the same thing we will see for the nonlinear thing as well. This is called as a reaching phase. The other one is called as a control phase. So you can see that the sigma has gone to the 0 and the corresponding state has gone here, and then it has gone to 0. So now what I'm going to see here, the beauty of the sliding mode control here. Now I'm activating this one. You can activate this one by double clicking this one. So now the sliding mode with the disturbance, sliding mode is activated here. The disturbance is activated here. I'm going to run this one. And now I will run these plots. So you can see that, so this is the surface, and you can see that, all the states have gone to 0. However, continuous chat, this is required. So-called chatted control input is required. And this is the sliding surface, sigma. If I particularly zoom this one, if I zoom this one, you can see that sliding surface has not exactly gone to 0. So what you can see that into 10 to the power of -4, which is quite reasonable. And if you want further, reduction on this sliding surface shattering, which in turn will have impact here, but there will be trade-off. So you have to select the various values of rhos and various values of alpha, what we have seen. So if you keep on changing various values of rhos and alpha, then your response, then you have this control chattering, the effect can be reduced here. So that is a parametric variation study, or parametric, the control parameter, the way if you keep on changing, so it will change, the magnitude and sometimes the frequency. This frequency can be controlled by using higher order sliding mode or approximation of the sigmoid function. So this is what you have to do it. Again, I'm repeating, you have to do 4 different simulations. One simulation, first of all, activate this linear and activate this 0. Run this one, whatever the results is getting. In the second case, leave this control law, linear control law, and see that with respect to the disturbance. In the second case, activate the sliding mode control law with without disturbance, and then activate this with disturbance. Run this, and you can see the response. You can then go for the plotting side. So I will be sending you the same, in the same format, 3 different files I'll be sending you. one, this time I will lock the PDF. So one Simulink file, one plot file. First of all, you have to run the Simulink file and then you have to run the plot file, otherwise it's not going to work. So Simulink skeleton file in both the formats, plotting file, and the third one is the PDF file. So please bear with me for 3 to 5 minutes. I'll be sending you, and we will meet. I'll be giving you the 20 minutes. So at 8:40 we will meet, and then we will see. We'll discuss a sliding mode controller, bug boost controller, and then where we will see how to implement this bug boost converter in that one. And actually, some healthy discussion is going on with me. Several participants have some disagreement with me in some aspects, or in other way, it is so some participants, those who are with the power systems background, so they are very hesitant to learn this power electronics. So they were saying that this example is not clear to us, whereas the vice versa, the participants who are working the power electronics, they are not interested.
Hello. Sir, myself
Hello.
Dr. Ponda. Sir, myself Dr. Ponda.
Yes.
Sir, I am power
Yeah.
system, but control system little bit I have read in the BTech, right, sir? So one question is that should I ask some questions, sir, to you now?
Sir, please let me complete my talk. I will give the slides this to the participant. They will keep on working. During that time, we can have the discussion. So just bear with
Okay,
me for
thank
5
you.
minutes. At 8:25, we can have the discussion. So that it will not be bothering to the other participants. Just give me 5
Okay,
minutes time, sir. I'll send this to the
thank you.
participants, and then we can have the discussion. Thank you. So participants, I'll be sending you the files. Please take a break for 3-4 minutes. Meanwhile, I will convert the slides to the lower version. I will send it to you in a couple of minutes. And at 8:40 we'll meet again.
Hello? Anyone is there?
Yeah, please tell, madam. Please tell. Hello. Yeah. Hello.
Hello, sir.
Yeah.
Sir,
Hello.
the file what you have sent, yes, sir, the file what you have sent now is linear and VSC, linear control for VSC. It is not SMC.
It is not SMC.
It was the
file is
previous.
No,
repeated, sir.
Same file is
Sorry.
repeated, sir.
Same file is repeated. Okay, okay. I will send. Just give me a minute. Okay.
Okay.
Okay, okay. SMC fundamentals. Okay, I might have given you the wrong file. Just give me a minute. That means people are at least opening and seeing, doing the things. Though it was my mistake, I will see. Sliding mode control. Is it the same file, skeleton of SMC fundamentals? Hello?
No, sir. SMD, no, those are okay, sir. The PDF what you have sent.
Oh, the PDF. Okay, okay. I was that one.
PPT.
Oh. Okay, just let me check. No, in the bottom it will be there. No, it is not there.
Sir.
The same 8 pages
Huh?
has come. I mean, the same 8 slides what we have discussed in the previous one have come.
Okay, 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 okay. Okay, that one you are thinking. Okay. Okay, okay. So I will do that one immediately and will send you in a minute. Oh, okay, okay. Now I got it. Yeah, I have sent now. The password is the same password. Some people have already received, already have. Okay, for the linear they have done. It is a password protected, the same password, what I mentioned earlier.
Sir, while executing, hello,
Yeah.
sir. We are getting U signal in between -2 to +2, but actually we are limiting the value of signum function between -1 to +1.
It is not, we are not limiting, sir. It is not the limiter.
Yeah,
The signum function is
actually,
different from the saturation, what you're seeing. The signum function has been
yeah, signum
multiplied with
function.
rho and x term as well.
Okay.
Yeah.
Actually, we need to get the value of U between -1 to +1.
Not u, it is the signum function, because your control is multiplied with rho and other terms as well.
The
It is
control
not
signal when
the no. Control signal is not the signum function. Control signum is a function of
I am not.
signum function.
Yes, sir. Yes, sir. I know that one, sir. Actually, we are getting the stuttering phenomena or the control signal is oscillating between the two values. That value must be in between -1 to +1. Sir.
No. It should not be. Why it should be between 1 and -1? So suppose if you are operating, a DC motor, whether your voltage will be between 1 and -1, or it will not.
Normalization case.
That depends upon the. No, normalization case, we are not doing any normalization anywhere, right, sir?
But
We are not doing
actually, in
normalization
majority
anyway.
cases,
If you do the normalization of control law, you have to do the normalization of the states as well of the plant, which we are not doing. Nobody does the normal. In majority cases, people don't do the normalization. Just it is for your convenience. You convert to the normalized values, but not always.
okay.
Hello, sir.
Yeah. Hello.
Sir,
Yeah.
I have a
Please tell.
small doubt. Sir,
Yeah.
while you were discussing, we have learned something called sliding surface.
Yeah.
Sir,
Yes.
exactly what this sliding surface is and what is the physical significance? Like, why is it so? I'm not
Okay.
able to clearly grasp what it is, understand what it is.
Okay. Okay. So here the sliding mode control, there are two different phases. One is called as a reaching phase, and another is kind of called as control phase. As a first step, what we try to do is we try to force your system to slide over the sliding surface. And once the system slides over the surface, then from there the sliding mode starts. So physically what they try to do is initially sometime, whatever when the reaching phase, uh, once the system slides, when the system states or the combination of the states slides on the surface, that is fine. But once it reaches, when the reachability condition satisfies, then it becomes then your system will become what I can say, that robust to the uncertainty. So whatever you keep the uncertainties, it will be trying to completely reject that uncertainty. So the sliding surface is a stable surface where which you want your the first of all you want your states you want to push, the control need to be designed in such a way that you want to push to that particular sliding surface. Since the sliding surface is a stable or the compensated system, once if you push your slides there, always it will be there. So that is the purpose. So physically, we cannot directly correlate this with anything, but systematic or in a mathematical way, two steps, you force, what you do is suppose some kind of model reference. There are the various way to design this sliding surface. One such way is suppose you assume that the output of the model, a very perfect model, is your is the reference model. What you try to do is you try to push your the states towards you try to push towards that sliding surface. And once if you reach a particular once as soon as you start sliding on the surface, and then once this reaching phase is over, then your system, reduced order system, or the regular form of the system will become uncertain, will become robust to the uncertain parameters. So it is a bit complex to explain in terms of physical things, but the thing is design the sliding surface and you should stable sliding surface. And always if you are in the stable sliding surface, then your controller will ensure that you will
Hello.
within finite time you can able to go to the thing. Yeah, hello.
Yes, sir.
Hello, sir. Hello.
Sir, Panda sir, only two questions per, that was the rule, sir. That was the rule of this FDP, that only we
Sir,
can take maximum two questions.
sir,
If you have
regarding
any
the
questions,
sir,
yeah,
one
if you have
minute.
any questions, please
Sir,
put it in the chat box, sir.
sir,
That is the
previous
rule of
question is
the.
okay, sir. Okay.
If you have, please put it in the chat box, sir. That is the rule of this FDP, so that everybody will get an opportunity.
Can I question, sir?
Yes. Yeah.
Sir,
Please introduce
actually,
Yeah.
sorry, sir. I am Savita Tripathi from Bhubaneswar, Odisha.
Yeah. Yeah. Please.
I have a question. I have done my MTech project on power quality improvement using PI and fuzzy controller of a
Okay.
sound active power filter.
Mm-hmm.
So I want to know how this SMC can help me to extend that work, extend my work.
First of all, I should. I mean, what? First of all, I should understand what is your work, man. The simple idea is replace the PID control with SMC and see, whether if it is robust to the, uncertainties and to the external disturbance.
Okay.
Hmm.
So I can replace my controller in that work with SMC.
Yeah, definitely you can replace, but you have to see whether after replacing or your earlier existing controller itself has some robustness properties or not. If not, then you can replace and see by giving various disturbances and various parameters, variations to see if sliding mode control is working better than your conventional PI controller.
Okay, sir. Sir, another question is whatever paper you have sent, that is 2009, whatever journal paper. So I want to know within these 10 years, that 2010 to 2020, there may be some more work on this particular field, whatever field you are discussing. So whatever I want to find if my work, whatever I'll do, that is a new one or not, so that I can publish my paper in that area.
Yeah. So here the fundamental idea of this workshop is to introduce the so-called famous control algorithms to the participants, and to give them the fundamental knowledge in this aspect, and to solve some fundamental papers, the base papers, and so that they could able to start from here, and they could extend this particular the concepts or the knowledge whatever they have gained to the advanced application problems as well. So there are many new things happening in this area. So if you have attended my first day talk or the first talk, I gave around 15 areas where the open areas in the control systems you can apply these techniques whatever you have learned in that advanced techniques, advanced applications, or you can go through the literature. That's what I can say, because this is very vast. If you say a particular area, then I can tell you what are the research opportunities in that one, because as such, as a whole, I cannot tell the whole world what the research is going on. Yeah.
Oh, okay. My area is actually I have done that work on power quality improvement using PI and fuzzy controller for a non-active power filter.
So you try to see, if what will happen if some of the sensors are faulty. Whether you are, for the PID controller, you are taking some measurements from somewhere, right? You make that sensor say 0 and see what you are getting. And if in the absence of some measurements, can your controller deals with them? If not, then that opens the venue for fault detection and isolation and fault tolerant controls. So that is one such area where you can explore. And in the fault tolerant area also, there are many ways to analyze the system. If your controller parameters itself, they are uncertain, then what to do? There are many such problems you can look into that.
Okay, thank you, sir.
Yeah. Okay, is the sliding mode is robust enough to model the disturbance? Yes, it is. It is to model uncertain or any kind of disturbance. That's what we have seen. Somebody has put the question. I think already the people have started getting
Sir, while writing the program in plots.m, here we need two variables for plot, but we have used only plot of states, comma, x variable we have not used.
Sir, that depends upon what version of MATLAB you are using. Suppose if you are using advanced version, then you don't need that one. So you can vary accordingly. So that plots file. Yeah. By default, it will take all. Yeah.
X variable it is not actually we have not given. That's why it is giving errors while executing in 2016. 2016.
Which
sir.
ones are? Yeah, plots. Which one you are saying?
Plots.m. That
yeah,
one
in that
actually
one, which plot?
Figure of one states only we have given.
Yeah.
But
yeah.
No,
the states are going to the workspace from. No, the states are going to the workspace. If you see in the simulation, the states variables are going to the workspace.
Actually, x variable we have not given. It is giving error, while only it is opening figure of one window. In the maybe 2006.
No. The plot should work for all such for anything, because there is no such some advanced thing in that one.
I think he had some problem in setting, sir. The structure with time array, some problem is there.
You can, sir, you can just
Yes,
use
sir.
your
Yes, sir.
plots of.
So that is the
Yeah.
array. If you convert, then that will do.
No, because by default it is there. Okay, you can different versions have different problems. You can check it, sir.
Yes.
As long as you are getting in the scope, the same thing you can, you know, you can, what are the variables, what are the
We
format
are
you're
getting
saying,
in
you
the
can say.
scope.
Yeah, the same thing, the
We
same,
are
whatever
getting
you
in
see
the
the scope. Yes, sir. You see the properties of
yes, sir.
properties of the workspace, accordingly you can do it, sir.
If they will use the array, it will be fine.
Yes, sir.
So I'm running out of the time. So I think I should start the next topic. So let me, I think most of you might have got, please, respond in WhatsApp or what I can say that, or in the app, go to meeting home. Yeah, I can see Sai Prakash has got, Ravi Kiran has got the linear. Somebody is getting some errors. Krishna Jyoti, SMC with disturbance. Good, 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 good. Hussein Sheikh, Rajesh Patnaik, yes. Use array, it will be fine, yes, okay. Okay, so what I will do now here is we will discuss a paper, 5 to 10 minutes only. And then what you have to do is you have to write the quiz. I will show you the structure. I will not give you the skeleton for this paper. Rather, I will give you the screenshot of the simulation, because now these two examples, I think, if I keep on giving the skeleton, then the learning will not be much. So I'll give you the screenshot. Let me share my screen, and I will tell you the paper what I'm going to discuss now. Yeah. So let's share my screen. Okay, I have shared my screen to all of you. I think it should be visible. And let me see whether it is visible to you or not. Yeah, okay. Okay, good. Okay, so today what I'm going to discuss here is I will tell you the fundamental aspects of this paper, how to do the simulation. There is another just a minute extension of this paper. So here he has used the non-minimum phase boost converter. In another paper, he has someone a author has applied the similar concept to the Kirk converter or the Cube converter. So let's have a discussion on this one. Okay, so let's see this one. So the paper here is a closed loop analysis and cascade control of a non-minimum boost converter. This was published in IEEE Transactions on Power Electronics, volume 26, number 4, April 21. So I will not go into much of the electrical point of view. I assume that boost converter, if you want to boost, the input voltage or something, you can use it. But what I'm interested here is, there are two states of this boost converter. This is I1 dot and V1 dot. and the everything, the remaining things you can see from this particular paper. What are E, what are L? Input voltage is the E, L is the inductor, inductor, C is the capacitor, R is the resistor, and other things. B be the output load voltage, and I is the inductor current. So the two states are, one is the output load voltage, and another one is the inductor current. So this is the one. Uh, so so if you see this particular diagram, what I can say here is basically it is a two loop structure. You can see it is a two loop structure plant. So here you can see that the inner loop is a sliding mode controller, and which is basically a current controller. And the outer loop, you can see that outer loop there is a PA controller, and in fact they have added the feed forward control as well. So in some cases, if this feedback control doesn't work, your feed forward control in the absence of uncertainty, or in the absence of if you know your system exactly and everything exactly, then in some cases this feed forward control will work. So this is the overall structure. This is the boost converter. Two states, the current and the output voltage, and the input U is from the sliding mode controller is going here. So what are the things required to simulate this plant? The first thing required to simulate this plant is to simulate the closed loop boost converter is these two equations, and you need the sliding mode controller, you need the PID controller, and you need the feed forward controller feed forward gain. So first of all, this is in the cascade control. So first of all, the outer loop control, and you can see that ID equal to VD square by RE. If you see this ID I star, so the reference current, how we are getting this reference current is, you can see the reference current is getting generated by ID plus IC. So ID is the feed forward current, so which is there is a constant gain here. You can see that VD square by RE, where R is constant, E is constant, and VD square will also be constant. So ID, it is a standard number, I will tell you. And this IC, how you are getting the IC? So what you are getting is you are taking this is the voltage, output voltage is compared with the reference VD voltage, and the error has been given to the PI controller, which in turn generates the IC current. So this based upon this IC and this ID, we are getting the reference current. And the aim of the sliding mode controller is to ensure that the error between the reference current and this actual current should be zero. So what is happening here is, if you think that there is no feed forward controller, whatever this ID is zero, then the output of this PI controller will become the reference control input. So this is one such thing. Okay, so what we need the PI controller. PI controller means only two gains is required. So the two gains are KP and KI. So this is one thing required, and this is my I star. So now I could able to get what is my reference current and the sliding mode current. So as we discussed that, S equal to this is a sliding surface, switching manifold. Sometimes it is called as a manifold as well. I minus I star. So this is basically the error in the currents. And my boost current controller, sliding mode controller, what we discussed. If S is less than 0 and S is greater than 0 and so on. So if S is less than 0, then this U equal to something like this. If it is greater than 0, then this becomes 0. So this is the sliding mode control. This is very much similar to the one what we have seen in the earlier lecture in the similar format. One is the linear and other is the non-linear. The linear action is only some constant value, and this sign is a non-linear. So now you have the complete information with you to do the simulation, and this is the further analysis. So if you are interested, you can go through the further analysis, or it is up to you. So the information what I need is, this is the controller to do the simulations. This is one such information is required. I need this PID PI controller, and I need this forward gain. So apart from the system equations, So where are all these parameters are given? All these parameters are given here. And to inform you that these are all the nominal parameters. So one such aspects of the sliding mode controller, what we have seen, there is disturbance rejections, but here we are going to see the effects of the parametric variation or the uncertainties. So these are all the nominal parameters, and one such simulation. So various simulation cases has been given. The nominal value. So these are the nominal value, and Kp and Ke value has given like this. So someone has asked whether to consider the negative Kp or Ke value. Yes, it is possible. You can see from this particular example, and they have done the real-time implementation as well. I will now go to, these are all the analysis. Those who are interested, they can go to this one. So I will show you the various analysis. What they have done here is, yeah, this is the simulation. So what they have done here is, these are the different parameters. You can see that, there is a change in 75% of EO. So where we have seen, we are only considering, so there is a 25% uncertainty. Earlier it was 20, now it is 15. And L, there is 20% variation. And C, 200% variation. C naught 8, and R, 500% variations. So I think earlier it was 40 and has become 200. VD is 35. And my ID, which is the feed forward control, is 0.41 amps. So all information, the parameters are in this section B of 6, and the table what we have seen there, we have discussed there, all the parameters are written there. So now what I'm going to show you is, I'm going to show how the simulation will look like and how it is going to work. I'm not going to share this simulation with you. You have to develop your own, but I will explain you the everything. So this is the boost converter, and I think my screen is visible. So what I will do here is, there are two different cases. You can use the same case. So what I will do here is, I will go with the nominal one. Sirisha, could you please be on mute? So this is the structure of my boost controller. So this F, the feed forward controller, you can see that U1 square by 40 into 20. I just hard coded everything here. This is not the good way. You can write in the parameter and that can be called here. So this is hard coded way. So this is one such nominal values. And these are the PI values, what he has used, minus 0.0087, 10.3. This is only P. The derivative term is 0. And these two are getting added to generate the reference current, and the actual current, the current is, which is from here you are getting, and it is getting separated to generate the sliding surface. And this is the sliding surface. If sliding surface, what we have seen from the paper, if S is greater than 0, your control should be 0. Otherwise, else the control should be 0.5 into 1 minus sine of S. This is the control law. And this is my boost converter. So here all the parameters, since this is the nominal parameters, I have given, E0, L0, C0, R0 as, nominal parameters. So if I assume that if uncertainty is 0, then it will take the nominal parameter. Else it will take, the uncertain parameter is 75%, 20%, 100%, and 500%. That depends upon, how you want to run the code. So here you can see that uncertain parameters and uncertainty. If you select one, it will take the uncertain values. Otherwise, it will take the certain values. I will just run this one and I will show you. Hopefully, it will run, because I did this simulation some time back. It's compiling, and yeah, it is ready. So now if I do this thing, so I can show you the voltage I have given here, that 35, and now it is nominal value. You can see that the performance of this one, it is going to 30, but with a lot of chattering. this can further be reduced, and this is the current reference current, and they could able to track. And the next what I'm going to show you here is in presence of the uncertainties, how it is going to work. In one such case, I ran this one. Now you can see that uncertainty is activated here. So now I'm going to show you what is going to happen here. This is the the thing. What I did is until 0 second, this time is going to inside. So as per the definition of the paper, I think until 1 millisecond, there is no control. So u equal to 0. So that's what I ensured here. Here I have ensured here, you can see that if time is less than 1 millisecond, then your control input is 0, because to replicate the results of the paper. So that is thing. And you can see the voltage, and you can see how the current is the reference, but there is some chattering. This chattering can be avoided by using the methods what I told. And this is your control input, because this is basically the duty cycle. You can see that it is limited between 0 and 1. This is a signal function, the fast switching action. And the similar results what I'm going to show you now here is what they got and what the results we have obtained. Yeah, this is the result for one such case. You can see the chattering here, and you can see that it is almost going in 0.1 second your voltage, and the current is approximately going to 0.5 and so on. So the similar kind of, so this is the first uncertainty with the system uncertainty. So they have done for various other cases as well. They have changed the input source voltage, step change. They have seen what is happening. They have changed the load resistance, and they have seen what is happening. They have the disturbance as well, input disturbance, and all other cases they have done. So various cases testing, and then they did the hardware implementation as well. So this is what we can see, and they have done the sensitivity analysis. It's all tests I have done, and it is working very fine with this one. So what I will do is I will share you this paper, and I will share you this screenshot only. Now it is your job to develop this one. Everything is given. It is quite simple, and so that is it from my side. And another paper, I will show you that paper. So those who are actively want to gain or extend their knowledge what they have learned in this thing. This is another paper. So again, structure is everything is same. Only the plant they have changed. They have used the converter, the same control structure. You can see that it is published a year after that one. So everything is the same. Here instead of the bush, they have used the converter, and everything is same. Instead of the 2 states, there are 4 states, and control law is also very much same. Control loop, you can see the same control law they have taken, and whereas the reference terms different values it is coming, and for equilibrium point, and the voltage again is a PI controller, the same thing they have used. All the parameters are given here. Again, it is they have done some classical analysis, and here they have shown the simulation with only one such the PI controller will tell you the what gains they have selected. They have selected the PI gains as 0.01, both KP and KA negative gains, and this is such results what they have shown, the transient and other results which you can which you can easily obtain for your particular case. So this they have given for the step change, different values of step change, the reference value. The V1 is going, I think, around 250, and then it is going to 150 and 250 various step changes, and they have seen the performance in this particular case. And this is the sliding mode control. So this the duty cycle, and this depends upon the capability of the switches what you are going to use, whether can you able to use this fast changing control signal for your particular plant or not. So this completes my today's session. Sorry, I extended it by 15 minutes. So now those who want to have interaction, I'll be here for another 10 minutes. And at 9:30, I'll be releasing the questions, quiz questions, and 10 o'clock, I'll be locking it. So it will be of 20 minutes. So another 10 to 15 minutes I'll be here to answer your questions. So the standard rule is not more than 2 questions from a particular participant. Thank you.
Hello, sir.
Yeah.
Sir, actually, the previous assignment what you have provided.
Nidamal.
Yeah. Yes,
Please tell, sir.
This assignment what you have provided, sir, the control program what function we have done, whether we have to include that signum based conditions.
Where, sir? Yes, you have to. That's yeah, that's what is the sliding mode control will do exactly.
But the code what you have sent is not having that, is that?
No, I have not given that. You have to write it, sir.
That is what I'm asking. Whether we have to write it.
Yeah, you have to write. I have given the skeleton only. I have not given the complete code because so that you will, it will be exercise for you. I have not given.
Yeah,
I have not given you the. Yeah, in the PDF what I sent, the exact thing will be there. You can just copy and paste there, sir. It will run.
No, sir. In PDF itself, you have let it. The sigma value you have not given that. Sigma value is provided as K2 plus C into X1.
Sigma equal to x2 plus c into x1. Yeah, it is there. Sigma equal to x2 plus c into x1. It is there.
Okay. Then that sigma conditions we have to write. No, sigma is less than 0. Then if sigma is that signum function we have to introduce there, sir.
Automatically, the signum function will automatically take care, sir. In this case, it is not required, sir.
Okay.
Sigma function, the MATLAB sign means MATLAB understands automatically. You don't have to write condition for this particular case. Yeah.
Okay.
Yeah.
Okay.
Yeah.
Thank you.
Yeah.
Sir, this is Satya from IIT Bhubaneswar.
Yeah.
Hello.
Yeah. Yes.
Sir. Yeah, I have a question. I have a question regarding the boost converter control which you have shown in the paper. If you have an parameter uncertainty or any kind of external uncertainty, so the frequency of your control signal will be variable, right?
Frequency of the control signal is variable. That depends upon the maximum. Yeah. You please complete your question, then I can answer. Yeah.
Because handling an uncertainty is something different from handling a normal nominal system. So my question is that the control signal will actually go to a switch, right? It's a power alternating device. It may be an IGBT or a MOSFET or what kind of switch. Is it not that you are varying the switching frequency, which will cause an issue? Because generally what happens is that in a power alternating device, when you're having it, you will always assume or you'll always have like to have. Hello.
Yeah. Please tell me. Yeah. Hello.
So can I go on?
Yeah. Please.
Can I go on?
Yeah, yes. Please.
For a power alternating. Yeah, for a power alternating device, we'll always assume that the switching frequency should be fixed value, because your filter design or any kind of design of the system will be decided by the switching frequency only. So in that case, like how do we have a trade-off in this?
No, there are various ways to to this chattering effect or whatever. There are various ways to handle this, and one such way is using the higher order sliding mode control. If you think that your system, your actuator doesn't have much capability to deal with high frequency signals, then you have to go for the higher order sliding mode controller, or you can go for approximation of the signum functions. So there is always a trade-off between, if you use the approximation of the sigma function, the chattering can be reduced, the high frequency, but it will have effect on the convergence rate. If you are going for the higher order sliding mode control, it has the capability to reduce the chattering, but it will increase the complexity, the system complexity, because higher order sliding surface, you have to higher order sliding mode need to be implemented. Yeah, so that is depend upon the plan problem at hand. That depends upon how you are designing this sliding mode controller. Yeah, so generally, if you don't want, that's what I'm saying. If your actuator has its own bandwidth, then you have to go for, if the frequency by using the normal sliding mode control, what you are getting is, if it is very high, then you have to go for the higher order sliding mode controls. Or you can filter out that as soon as if you keep the filter as the output of the controller, then what it will do is it will give you the filtered response, but at the same time there will be delayed response as well. So everything will be fine. You will be getting the chatter free controller, and you can still able to deal with the uncertainties or disturbances. But there will be a trade-off, is that your system will become a little bit slow if you use the filter in front of the controller output. Yeah, I'm done.
Yeah. Okay. Okay. Okay.
Yeah.
Hello, sir.
Yeah.
Sir, I'm Bhanu.
Yeah.
Sir, in the sigma, for this one, you have actually considered x2 plus 3x1. And
Sorry,
there is
x2
again
plus.
a relation
Yeah.
3x1.
Yeah. Yeah.
Now, instead of x2, I take a matrix.
Matrix.
I mean,
Okay.
Yeah. So, is it C is always a constant, or what is it exactly?
Which one? C value.
Yes. Because
The C should
x2
be
is
the
again
constant.
x1
The
dot.
C. Yeah.
So x1 dot plus C x1. This is what we have taken as sigma.
Yeah. Yeah. If you see that, if you take it the C on the right hand side, so what is going to happen? X1 dot equal to minus C into
C
X, isn't it?
Yes, sir.
Okay. So if you find the solution of that one, it will be exponentially decaying function. If you take if you integrate that one, and C is
Yes, sir.
basically
E power minus. Yes, sir.
yeah, e to the power minus. So it will be always be a exponentially decaying function, isn't it? Based upon the pole where that C value you're going to place. If the C is positive, that's why you have to take the C positive. Then only the exponentially decaying function you will get. If you take the C negative, then it will be exponentially increasing. So that will make your system unstable.
Okay. So my question is, suppose this x, it's not a single variable. Like in this x itself, suppose x1 itself, x1, x2, x3, it is having more number of
Fine.
states.
Then then it will become a sliding surface, not the sliding variable.
Okay.
Then it will be the surface. So that is called as a sliding manifold or sliding surface.
So then this
Surfaces,
C is, we can take this C as a constant also, na, sir?
You can take the C as a constant positive, because constant multiplied with the vector, again it will be the vector only. Otherwise, the depends. C tells you about the convergence state. Okay, if you have 10 states, if you want some of the states to converge fast, then what you had, you please mute Vasu, or somebody please mute. Somebody is discussing in the background. So if you take the single C, then the convergence rate of all the system will be the same. That I don't want, right? Sometimes I want the faster convergence for one state, and so during that cases, what you have to take the diagonal matrix with different C values, and each C values you have to define based upon the particular state convergence requirement of the state. If you want very fast, keep the corresponding C value in that matrix as very far away from the origin. If it is not of much important, then you can keep the poles at near to the origin, that C value near to the origin. So that
we
works.
can place a very large value to make the system very fast. Is it okay, sir?
You can place it. No. The practical consideration is, if you are placing the pole very far away, the system will be very fast. However, if you see in the frequency domain, what will happen? The bandwidth will be very large. You're designing for a very large bandwidth. If the bandwidth is large than the high frequency, that means you are allowing higher frequencies. The higher frequencies might contain the noise. So here you have to restrict yourself to based upon the problem at hand. You cannot place. And secondly is, you cannot place the pole very fast due to the actuator limitation. Although you are placing a pole at minus infinity, which will give you almost zero time, t equal to very small value, but your system has inherent the inertia or something, which will, even though control theoretically it happens, it will not it will not happen.
Yes, sir. And the selection of V, actually, this V dot, I mean the Lyapunov function, negative definite function. So you are actually subtracting minus Cx2 plus V. I mean,
I'm not in front of that I mean
okay.
slides now. You can tell
Actually,
just I will try to because I'm typing.
my question is, sir,
This
minus
is the last
sigma.
question, Bhanu, for you. This is the last question.
Okay,
Yeah.
so this is the last question.
Yeah.
Minus rho sin signum function of sigma is what we have taken as v or u function, sir, or not u.
Sorry.
Sir, as signum function of rho, if you see that. Actually, I just made the derivation on my own.
If it is very specific, then you can put it in the chat box. Then accordingly, I will for the sake of other participants, if it is very specific questions, then you can keep it in the chat box. I will answer because we will give the others as well the opportunity to clarify their doubts. If it is very specific, please let me know. Otherwise, you can keep in chat box and I will be answering that one.
Thank you, sir.
Yeah.
Hello, Satya from IIT. Hello.
Okay. Yeah, this is your second last question, Satya. Please tell sir.
Yeah, I know.
Yeah.
It's just an extension.
Yeah,
It's just a clarification of my earlier question. It's fine. It's fine.
Yeah.
The thing I asked is, it's not about reducing the chattering effect. See, for example, for the same design of SLC, not going for higher order. So the frequency of your control signal is varied. It's variable. Getting my point, sir. When you have an uncertainty, it is a variable thing. So you cannot exactly say that when you deploy the controller onto the converter. So you cannot exactly say whether you are switching frequency. That means the control signal is going to the switch, which decides the switching frequency. It will be constant. But in no converter, as far as I know, will be operating on a variable switching frequency for a switch. I not get that because you understood my question in the other.
Okay. So let me answer your question. So before real time, if you implement any of the controllers, you should be knowing ahead what is the switching frequency. Switching frequency. So the controller, if you see the background, if you do the reverse engineering, if you know what is the maximum switching frequency your system can take, switching frequency, let us assume it's 10 kilohertz or so on. So now you come back and redesign your controller in such a way that you should not see the maximum switching frequency. I'm not talking about the chatting. I'm talking about the switching frequency, what you were saying, which will, switching frequencies or the kind of duty cycle. Let us assume that duty cycle is the one which is going to your plant or so on. So that again depends upon the design specification. Sometimes we design the controller to take care or to handle that is based upon a particular application, whatever it is, all electronics. You may be knowing what is the switching frequency of your systems or what are the switching frequencies. Based upon that, we'll do the reverse engineering and when we'll design the controller in such a way that it should not see the maximum or maybe that up to the 80% of the allowable or the maximum switching frequency, whatever is possible. We will design accordingly before itself. So otherwise, for the safe side, we will not we will not see the maximum switching frequency possible for a particular system, or we will design a system in such a way that control systems, closed loop system, which is in our hand by varying rho, sigma, and different k values in such a way that it should not see the highest highest component of the thing. There is always a trade-off here. What I will suggest is you might be seeing the control signal if you simulate this particular power electronic device. You can see the switching frequency, what is happening, and you can see that if you change the value of rho, and you can see what is happening to that. So rho and the another parameter is alpha. So these two play around with the switching frequencies as well as the what I can say that the chattering as well. So these two parameters you can keep on changing, and you can see, without for one particular combination of rho and alpha, what you are getting. You can tabulate this one, and you can always see what is the control input, the frequency of the control input. You can see what is the maximum frequency component. If you want, you can use the FFT analysis to find the maximum frequency component. You change this rho, you change this alpha, the combination of both those things, so that will give you, the intuitive feeling of how to control or how to have the switching frequency less than or less than whatever is the maximum possible for a system. So again, that depends how you change the value of rho and the alpha. These rho in some cases can be as small as micro or nano or pico, but in some cases the rho can be as large as 10 to the power 6 and 10 to the power 12 based upon the problem at hand.
Okay, sir. Okay.
Hello. Yeah. Hello.
Hello.
Hello, sir.
Sir,
Yeah.
good evening, sir.
Yeah. Good evening, Mujir.
Sir, actually, you have mentioned about the chartering, no, sir, in the sliding mode
Yeah.
control regarding the high
Yeah.
frequency component. So to avoid that, we need to change the values of rho and sigma such that it has to be minimized like that.
The rho, yes, there will be little bit effect in that one, but if you want to reduce, really, if you want to reduce that signum function, how you are writing that signum, right? Instead of the actual signum one, you can use the normalized signum function. If you see the papers by Krishna Edwards, in the denominator, what they use is plus some small value they add. That small value will tell about the bond of where it is, the range of or the band where it will be settling. If you take very less value, so in the denominator, if you just add some small value, then it is a trade-off between the chattering and the convergence of the thing. That is one thing you can do it. That means approximate the sigma not to the actual switch. You can what I can say the sigmoid function. If you can approximate the first order sigmoid function, so the chattering will be reduced. That is the classical way of doing things. Second thing is you have to go for the higher order sliding mode control.
Okay, sir. One last question. This is the last question I am about to ask. So, whenever we are moving on to the higher order system, so to what extent we can go, sir? And what is the stability? I mean, can we maintain the stability if we move on to higher order systems?
Yes, the higher order systems, basically it depends upon your computational power available with you. If you are going for the higher order system, then it will make your systems very complex, whether if you have that much fast processor with you or not. If it is there, then yes, that again depends upon based upon the processors available. So it is not that there is, you can go to second order, third order, fourth order sliding order, but that depends upon what is your requirement and what is the available, the actuation power, the computational complexity, and all other things.
Okay, sir. Thank you, sir.
Hello, sir. This is Vasu, sir.
Yeah, Vasu, please, sir. Yeah, Vasu,
sir,
please.
I have a question like, sir. I have a question like you have said that to improve the effectiveness of the sliding mode control, we have to improve the order of the control. Sir, if the control order is more than the system order,
No.
is that in a real time?
It is. Yeah. Please continue. Yeah.
If the controller order is more than the system order, is it in real time? Is it acceptable one, sir?
That
Because
depends
if
upon
system
what you are
having
using. Yeah. Let me answer that one. And that depends upon what you are. There are two ways to do that thing. The first way is the techniques called as model order prediction. Either you can, in general, if you see this is not the case for the sliding mode control. There will not be much order, change in the order that you can. There is not this order. It will not drastically change. Unlike in HFD controller, where your system can be second order and based upon the weights, it can go to up to 10th order or 5 times. But that will not happen in the case of the sliding mode controller. But in general, if the order of the controller is very high, then you can go for the sliding mode. The model reduction by using the Hankel norm approximation or so on. So there are many ways to handle this situation.
Okay.
Actually, you want to see what what you exactly what is your requirement. Suppose if you says that my system is quite stable and quite uncertainty is very low, I don't mind, my parameter variations are very low, then you can go for very simple, simple PI controller. But if you demand more, it should be able to handle all kind of matched uncertainty, and it should be able to reject all kind of disturbances, bounded disturbances, and everything. Then there is a trade-off. So that's what I'm saying. That depends upon the plant at your hand. So what you want and the desired, what is your desired specifications. So that's why not a single controller will serve the whole world problem purpose. Yeah.
Okay. And final question, sir. And the effectiveness of this SMC will mainly relies on that developing of a sliding surface. What I understand
Yes,
from the previous question.
there are many ways to design the sliding surfaces. I have just shown you the linear sliding surface. There are, if you want very fast convergence, if you want your system to reachability phase very fast, then you can use the non-linear sliding surface as well. You can see one of my papers which we have designed in 2010 VSC with Bandopadhyay and other people. So where what we have done is we have taken the non-linear sliding surface and we have shown the convergence is faster if you use the non-linear sliding surface.
Okay, okay, sir. Okay, sir.
Yeah.
Thank you.
Yes. So anything else? Otherwise, we'll wind up the session. And tomorrow I'll be discussing the observer concepts, the more specifically the Leuenberger observer and sliding mode observer, and some of the properties we'll be discussing and how to design other things. We will take 1 or 2 papers as well. Yeah. Anything else? Otherwise, we'll wind up the session. And you can expect the quiz questions to be, you'll be receiving the quiz question in another 5 minutes and half an hour time whenever, whenever the quiz reaches to you, it will take, I will keep it open for half an hour. Okay, thank you very much. So please, all of you, please respond to this quiz. It is very important, though it is in the late night. So please, try to. Sabita, do you have any query?
Sir, it will come in a link, na? Sir, the quiz question
Yeah,
will come from link.
Yeah, not mail, sir. Only all communication will be in the WhatsApp itself, sir. In another 5 minutes, it will be there by 9:45.
Okay. Thank
you. Yeah. Okay, so I hope everything is fine. So we will discuss tomorrow the sliding mode observer and the Leuenberger observer. I will just give you the philosophical introduction. In general, the Leuenberger observer is only designed for the systems where the main purpose is placing the observer poles at the desired location. It is the dual of the pole placement controller, whereas the philosophy of the sliding mode is completely different. And we will see tomorrow, what is sliding mode control, and then afterwards I will discuss the fault detection and the reconstruction. If there are some sensor faults or actuator faults, how to reconstruct, because if you know the fault accurately, then you can either you can directly cancel it or you can design the fault tolerant control very accurately. So that will be our another interesting topic what we will be discussing, which is a bit different from the conventional control topic what we have till now, what we have discussed. So there, slowly we will be going towards bit challenging topics. So similarly, the simulations level will also, the first 2 days, the first in the FDP, what I can say that the revision which I did on 1 week before, so that was a very fundamental thing, and slowly we were asked to do the 2 area systems, which is a bit tough. And today I have given you the enough input to design the sliding mode controller for a toy problems or for a very simple problem. And from next onwards, the difficulty level will slowly increase, so that so that it will be helpful for your future research as well. Because if we keep on solving only the toy problems, and if I give all the inputs kind of spoon feeding, then the learning will be less. So now onwards, the difficulty level, slowly. Earlier I gave you everything to copy paste, and the next I gave you only the Simulink file with missing things which you have to fill. And so like that, slowly we will keep on increasing. We'll increase the difficulty level so that it will be good learning for you. You might strive hard, you might struggle, you might bang your heads with the infinite switching frequencies. So that is all what you have to do to, you have to go through various tough tasks to become, the beginner to expert. So that's what this FDP is meant for 2.0. You may not be in this 1 week, it is almost impossible to become expert, so-called expert, but at least your learning level will be enhanced learning. You'll be having the enhanced learning level. So with this, I'm concluding this thing. I'll be waiting for 1 more minute if you have any queries. Otherwise, I will end up this session and I'll be sending you the queries, the quiz in a minute.